Have you ever really looked at the world around you? I mean, really looked? It's filled with shapes, buildings, honeycombs, even stop signs. But what if I told you there's a simple, kind of secret math that connects all of them? Well, today, we're going to pull back the curtain and uncover the elegant rules that govern the hidden lives of polygons.
I mean, just think about it. From the little pieces in a puzzle to the massive structures in our cities, polygons are pretty much the basic building blocks of our world. They're like an invisible blueprint for everything, and they all have to follow a very specific set of rules.
So, what is this hidden math, really? How can a simple three-sided triangle have anything in common with a big eight-sided stop sign or the perfect hexagons in a honeycomb? The answer, you'll be happy to hear, is surprisingly simple, and it all begins with the most basic shape there is.
That's right. The answer to understanding all of these complex shapes starts with the humble triangle. It's the first shape we all learn about, and for really good reason. It's basically the key that unlocks all the others.
You know, if there's one thing most of us actually remember from geometry class, it's this one rule. The three angles inside any triangle, doesn't matter if it's big, small, skinny, or wide, they always add up to exactly 180 degrees. This is our starting point, our North Star.
Okay, so that's great for triangles. But what about something a bit trickier, like this pentagon? It's got 5 corners, 5 sides, 5 angles inside. How does our 180-degree rule for triangles help us figure out the total for this shape?
Well, the trick is actually kind of brilliant in its simplicity. We just slice it up. We take this complex polygon and we chop it up into the simple shape we already understand. All you have to do is pick one corner, one vertex, and just draw lines to all the other corners you can't already reach. And just like that, any polygon becomes a nice, neat set of triangles. And that special line we're drawing? It's got a name, of course. It's a diagonal. All it is a line that connects 2 corners or vertices that aren't right next to each other. It's this simple little line that unlocks the entire puzzle.
All right, so we've got our secret weapon, the diagonal. Now let's see what happens when we start using it, because a really powerful pattern is about to reveal itself, one that lets us create a universal formula for pretty much any shape you can dream up.
Just look at the pattern here. A triangle has 3 sides, and it gives us, well, one triangle. A quadrilateral, any 4-sided shape, splits into 2 triangles. A pentagon with 5 sides splits into 3 triangles. You see it, right? The number of triangles you can make is always exactly 2 less than the number of sides.
And that little observation right there gives us this incredibly powerful formula. For any polygon with n sides, as long as it's convex, which just means all its corners point outwards, the sum of its interior angles is simply n-2 times 180 degrees. That's it. This one formula works for a square, a pentagon, even a shape with 1,000 sides.
So theory is great and all, but the real fun is actually using this thing to solve puzzles. So let's put our new theorem to the test.
Let's kick things off with a classic octagon, just like a stop sign. It has 8 sides. So we plug 8 into our formula, where n is. That gives us 8 minus 2, which is 6. Then we just multiply 6 by 180, and we get a grand total of 1,080 degrees inside that shape. It's that easy.
What's really cool is that we can also use the formula to play detective. Let's say a mystery polygon has an interior angle sum of 900 degrees. Okay, so we just work backwards. We take 900 divided by 180, and we get 5. That means n minus 2 must equal 5. So what's n? Just add 2, and you get 7. Our mystery shape is a heptagon.
And this is super useful for finding a missing angle in a shape. For any 4-sided shape, a quadrilateral, we know the total has to be 360 degrees. So if you know 3 of the angles, all you have to do is add them up and subtract that total from 360 to find that last missing piece of the puzzle, x.
Okay, so we've totally mastered the inside of polygons. But what about the angles on the outside? This is where a truly surprising, almost magical rule shows up.
Seriously, get ready for this. We just saw that the sum of the interior angles gets bigger and bigger the more sides you add. But the sum of the exterior angles, it stays the same. It does not change. I don't care if you have a triangle or a shape with 100 sides, the sum is always the same.
And the proof for this is just beautiful. Imagine you're taking a walk around the perimeter of any polygon. Every time you get to a corner, you have to turn, right? That turn you make is the exterior angle.
Now, if you could just snip off each one of those angle turns and piece them all together, they would fit perfectly to form a complete circle. And how many degrees are in a full circle? Yep, 360 degrees. That's the magic number. For any convex polygon, the sum of all its exterior angles is always, without fail, 360 degrees. It's this incredible, simple constant that's just hiding there in all that complexity.
So now let's bring it all home. We've got the rules for the inside angles and the rules for the outside angles. What happens when we look at those perfect shapes, the ones where every side and every angle is exactly the same?
So these perfect shapes have two key features. First, they're called equilateral, which is just a fancy way of saying all their sides are the exact same length. And second, they're equiangular, which, you can probably guess, means all their inside angles are also identical.
So when a polygon checks both of those boxes, it has equal sides and equal angles, we give it a special name, a regular polygon. A perfect square, an equilateral triangle, the octagon of a stop sign. Those are all fantastic examples.
Here's a great real-world example. A trampoline shaped like a regular dodecagon. What a great word, right? It just means it's a perfect 12-sided polygon. All 12 of its sides are the same length, and all 12 of its angles are exactly the same.
So let's run the numbers. The total sum of the interior angles is 12 minus 2 times 180, which is a whopping 1800 degrees. Since all 12 angles are equal, we just divide 1800 by 12, and we find that each interior angle is 150 degrees. Now for the exterior angles, the total is always 360, right? So we divide that by 12, and we find each exterior angle is exactly 30 degrees.
And that leaves us with one final thought. An interior angle and its exterior angle always sit on a straight line, which means they have to add up to 180 degrees. So if I asked you to find the angles of a regular 30-sided shape, what's the fastest way to do it? Would you use that big, kind of clunky interior angle formula? Or would you use that simple, elegant exterior angle rule as your shortcut? The answer really shows you just how beautifully connected these inside and outside rules really are.